Welcome again to the course on audio signal processing for music applications. In the previous theory lecture, I gave an overview of the field of audio signal processing as an introduction and motivation to the course. Now I want to outline the specific topics that we will present in the course, which, even though cover a tiny part of the audio signal processing field, they are very relevant to understand many concepts and methods used in audio signal processing systems, especially the ones for music applications. As introduction to the course, this week we have given a context of the audio signal processing field, given an outline of the course, and we will go over in the next class over the basic mathematics that are required to follow the course. Then next week we will start by introducing the discrete Fourier transform. This transform is the basis for everything we will do, and we will try to understand every component of it. So we will go through the DFT equation, then we will go through complex exponentials, the scalar product in the DFT of complex sinusoids, the DFT of real sinusoids, and we'll finish with the inverse DFT, so to reconstruct the original signal. Then in week 3, in order to better understand the DFT, we will go over the basic theorems and properties of the Fourier transform. And these are the concept of linearity, shift, symmetry, and convolution. Then we'll talk about energy conservation and decibels, the concept of phase unwrapping and zero padding, the use of the fast Fourier transform, which is the algorithm that we will be using to implement the DFT, and then the FFT together with the concept of zero phase windowing, and finally we'll put it together into an analysis synthesis system. So then on week 4 we will go to the short time Fourier transform, which is the first version of the Fourier transform that can be used in real sounds, thus on signals that change in time. We will present the first complete analysis synthesis system of the course that is of some practical use. So we'll start with the STFT equation, then talk about the analysis window, then about the FFT size and hop size, then the very common concept, which is the time frequency compromise, which is fundamental to understand the short time Fourier transform, and finally we will discuss the concept of the inverse short time Fourier transform. So with that we can put together an analysis synthesis system. Then on week 5 we will go a step further, and we will be building on top of the short time Fourier transform what we will call the sinusoidal model. We will present the equation of the sinusoidal model. Then we will introduce the concept of what are sinusoids seen from the frequency domain, seen from the spectrum, and then we will talk about how we will actually find those sinusoids, and the concept is going to be the idea of spectral peaks. And then we will talk about how to analyze, identify these sinusoids as time varying sine waves in the spectrogram, in a time varying spectrum. And finally, again, we'll talk about synthesis. So again, building up an analysis synthesis system based on this concept of sinusoidal modeling. Then the next week, on week 6, we will be assuming that sound is harmonic, and then if we do that assumption, we can develop a much more powerful model, what we will call the harmonic model, which is a sinusoidal model in which we add the constraints that all the sinusoids are multiple of a fundamental frequency. So we'll introduce the harmonic model equation, then we'll talk about 3 concepts that many times we confuse, which is the concept of sinusoids, the concept of partials, and the concepts of harmonics. Then we will introduce the concept of monophonic and polyphonic signals, because the analysis techniques we will be using are quite distinct if we apply them to monophonic or polyphonic signals. And finally, we'll talk about how to detect the harmonics. To do that, we will complement this discussion with the idea of fundamental frequency detection. A harmonic sound is one that has a fundamental frequency. So we need to understand these and be able to implement techniques to analyze the fundamental frequency. Then on week 7, we will add some more complexity because many sounds cannot be well modeled with sinusoids or with harmonics. So we need to worry about the parts of sounds, attacks, nonlinearities, noises that are not well modeled with sinusoids. And for this we introduce the idea of modeling sounds with sinusoids plus residual. And in that concept we need to introduce the concept of stochastic model, so how signals can be modeled using this concept of stochastic signals. And then we will actually talk about how to approximate sounds with these stochastic models. And then we will introduce this model of sinusoids or harmonics plus residual. So the signal that is left that is not modeled well with sinusoids and harmonics. So therefore we will need to talk about subtracting this residual, obtaining this residual. And then this residual, hopefully, in many situations can be a stochastic signal, and therefore then we can present this sinusoidal or harmonic plus a stochastic model. Therefore, for that, we will need to introduce the concept of how to model the residual with this concept of stochastic signals. So in this will be quite dense lecture because we will be talking quite a bit about very different models and that complement each other and that can be a little bit complex to understand at the first approximation. Okay, and then basically that's going to be all the models we will be talking about, and in the rest of the classes, the next 3 classes, we will basically talk about applications and more kind of advanced topics. So as I mentioned in this course, we focus on 2 types of applications. One is sound transformations. So in this week 8, we will go over the models that we have presented and show the types of transformations that are possible to do with them. So for example, we will talk about the short-time Fourier transform and what can we do in terms of transformation, so specifically filtering or morphing. Then we will go over the sinusoidal model and what type of transformations, basically focusing on time and frequency scaling. Then on the harmonics plus residual model, we will focus on the idea of pitch transposition. And finally, on the most elaborated model that we will have introduced, which is the harmonics plus stochastic model, we will talk about time stretching and morphing. Then on week 9, we will talk about the second major application we would like to focus on in this class, which is the idea of sound description. So with what we have presented, we can extract features of a sound in a way that are relevant to describe it. So we'll first focus on the idea of audio features that can be obtained from this spectral analysis that we have talked about. And then we will talk about how to use these type of techniques to describe more complex music or signals and concepts of like a whole collection of sounds. How do we handle the analysis of not just one sound but a collection of sounds? And finally, on the last week of classes, on the 10th week, we will review all the models and outline related topics that we have not been able to cover in class. We will present other Fourier-based sound models, and we will also present other models that are not Fourier-based. So again, we will review the class and then go beyond these signal processing for music applications, things that we have been talking. And that's all. In terms of references, as in every class, all the content is available online and with open licenses, so feel free to review all the content and have access to everything I have been mentioning. So this is all for this lecture. We have done a quick outline of the course, going over the theory topics that we'll cover. So from now on, we are really starting going into signal processing. So thank you for your attention, and I'll see you next class.